Hello everyone, this is Junhan from Delft. Today I will be sharing our newly published dataset, The Growing Strawberries. This is a story about computer scientists spent years in greenhouses. We brought cameras to the greenhouse, we set them up, locked them, and let them take hourly images about how the strawberries are growing there during 2 years of cultivation in 2 different greenhouses. In the end, we got a video like this. We screened out the bright and clear images, we sent them to rounds and rounds of annotation and correction, and after that, we got a growing strawberries dataset. A GSD object looked like this. It records the growth of strawberries from a baby to a mature red one. As already hinted by the title, this is a multiple object tracking dataset. Each sequence of GSD carries the cultivation of strawberries in a year, so it is a very long-term tracking task. And more importantly, what we are monitoring is what's happening in the real world. So, in a nutshell, the GSD is a long-term multiple object tracking dataset that monitors the growth of strawberries in the real world. The GSD was collected by pairs of cameras. Each pair has one RGB camera and one OCN camera. The two cameras are placed in parallel, so most of the views are overlapped. The preliminary plan of using the OCN cameras is to provide more information outside of the visual spectrum, but also in an affordable way for the future users. Nevertheless, as they do not provide a lot of more extra tracks, by setting up bounding box association and image matching algorithms, they could, in the meantime, help with the correction of the tracking task. By comparing our dataset with existing mode datasets, we argue that there are two challenging points that are not explicitly addressed in the field of multiple object tracking. For one thing, the strawberries keep developing during the monitoring time. Therefore, the appearance that were recorded in the sequence keep changing. For another, as there are inevitable horticultural activities such as harvesting and repositioning the strawberries. Under a low frame rate that suits the data collection over such a long time span, the movements are recorded to be very irregular. Hereby, we will show a few examples to quantify those challenges. We identify the appearance of strawberries by its color. We use the hue from HSV color space to quantify the intrinsic color. The hue ranges from 0 to 1, defines the color in this rainbow circle. We randomly select one object from the GSD dataset and one of the Mode 20 dataset, a very famous one on Mode Challenge, by plotting the hue value from their observations. We could see there is a very significant jump at around the 90th frame in the GSD object. However, the hue of this MOT20 object is much more consistent along the frames. We also collect the hue value of all the observations from the bounding boxes, and then we plot the distribution of them. As you can see in this plot, the color of the GSD objects are quite concentrated to two values, which are essentially green and red. However, as the Mode 20 dataset cares about pedestrians who can be with very colorful clothes, the distribution is more spread out over the color in this rainbow. It also indicates that by the pixel color, it is much easier to identify person to person, but not from strawberries to strawberries. We quantify the object movements by the intersection of union of one bounding box to its previous association. We gathered the movements by the trajectories and calculate the standard deviation of the IOUs along this trajectory. Then we plot the distribution of those standard deviations. As you can see in this graph, the GSD tracks have an overall higher STD of the IOU compared to the Mode 20 trajectories. We also plot the object movements regardless of the track. As you can see in this graph, the movements observed in GSD are more spread out. And interestingly, We see a little tail, but only in the GSD movements, indicating that there are a few movements that are too radical that the two adjacent bounding boxes have even an IOU less than 0.02. Of course, we implemented and benchmarked a few state-of-the-art multiple object tracking algorithms on GSD. More details can be seen in our paper or our poster session. But with this presentation, I would like to show a very interesting way to evaluate the results, called the application-oriented evaluation. This is to assess how good the algorithms are in doing this specific task, tracking the growth of agricultural objects. This evaluation was conducted based on the proposition, as we all know, strawberries grow from green to red. In this task, we consider another color space, called the C-lab. There are 3 channels from the C-lab color space. The L channel describes the brightness of an image. The A channel ranges from -100 to 100, indicating the color from green to red, as you can see in this horizontal axis. The B channel described from blue to yellow. Essentially, the angle of every point that you can find in this circle is again the hue. But in this case, we visualize the color change by the A channel of the observations, because the color exactly quantified the color change during the biological development of our object, the strawberries. A curve for such a growth from green to red looks like this. For this evaluation task, we selected the tracking results from StrongSort, which had a combined using of the motion information and the appearance features. We associated the tracking results to a ground truth bounding boxes so that we could plot again on the same curve. So, let's see how it works. For this strawberry, the track number 40 described most of its life, mainly from half red to fully red. There is another track, number 15, described the life when it was still green, until there are some red started to occur. During the growth, there are a few moments that the strawberry will actually recognize as another strawberry, the number 21. That one has been red for a long time at the moment of switching, but this strawberry is turning from green to red. I suppose they might have some similar shape, or the green strawberry might have a similar area of red elements in the pixels. On top of that, when the strawberry was very, very young, probably it was still a baby in the flower. It was recognized as another track, called number 5. So, altogether, the same strawberry was recognized as 4 different strawberries by this multiple object tracking algorithm. The results indicating that the matrix ID fragmentation is valued as 4 for this tracking, and there are 2 ID switching happening in the tracking results. Therefore, if we'd like to use these tracking results to check how many strawberries are growing and how good they are growing, we might eventually obtain a report that's showing that we have 4 times of strawberries than what we actually have. In total, we benchmarked 5 state-of-the-art multiple object tracking algorithms on GSD. There were 2 from the motion-focused family, 2 focused more in object appearance, and 1 end-to-end algorithm with a graph neural network. For more details about the experimental result and what we've learned from that, please refer to our paper or come to our poster session in the 3rd day of WACB. Our poster is crafted with heart and passion. It's like a beacon of cuteness that you can't just miss in a crowd. In short, with this presentation, I would like to give you an impression about the growing strawberries dataset in a nutshell, and the challenges that brought to the table by the appearance change of objects and irregularities in object movements. Do we hope that GSD could motivate motor research to focus more on strawberries? Yes, but no, because the 2 challenges can be shared by many other objects that keep changing over time. The dataset is published by TU Delft and Burst.ai, and the 4TU data platform takes the responsibility for data maintenance. The latest version is accessible by this QR code or with this short link. Thank you very much for listening. and wish your next strawberry to be very tasty.